right, welcome back. So today we're going to do a couple things here. We are going to explore numerical quadrature. If you remember last time we talked, last couple lectures, we introduced this idea of numerical quadrature from a very broad perspective. Today we're actually going to do a hands-on example and sort of look at the implications and how it works and try to expose ourselves more to it. I then want to cover something called defeaturing of CAD. This is a common problem. I think I have alluded to it in the past here, but I just want to show some slides and sort of talk through that again. As you transition from CAD models to finite elements, you have problems many times, and I wanted to talk about that. We're then going to further our theory discussion on higher order elements. We are at the stage where it's kind of difficult to write all these equations out. It gets too complicated, but we present sort of the framework of these elements to add to our library. And then finally, we're going to end by studying something called element locking and hourglassing. In Abacus, you've seen us select the hourglass option. We did that in the last application where we selected the hourglass control. And so we want to actually understand what that means and why is it important for finite elements. So we're going to do that today. So let's get started. Okay, so if you recall from the last couple of lectures, we have introduced the four-noded quad element. And we went through the whole derivation of the element stiffness and all of the internal calculations. And we saw that, at least for the element stiffness, we got to a point where those integrals that we typically do over the element, remember we break up the total potential energy into smaller integrals, they were left with terms of psi and eta that could not be evaluated. And so it's not like in the, for example, the truss, the 1D truss, we had the integrals will evaluate to a real number. We didn't have that. We were actually left with variables that we didn't know. And so we basically have to come up with approximations to these integrals. Okay, from -1 to 1, we have two integrals here because we have two directions, two degrees of freedom. And we have to come up with an approximation, and what we do is we're going to use Gauss quadrature, Gauss-Legendre we called it. And we're going to put Gauss points or integration points at these locations in the element, and mathematicians have derived equations that we can use. We can plug in the location of our natural coordinates. We use something called weights, and you plug that in and evaluate the function at those values, and then you're left with an approximation to the integral. So this is out of the textbook, and we went over that last time. What we want to do here now is actually go into a couple problems. I have a Gauss notebook. This is a program called Mathematica. It's great for evaluating equations symbolically. And then we have a problem in MATLAB that kind of looks at this a little more in depth. So we're going to cover this on a hands-on example. So now what we can do is jump over to the portal and get these files from Canvas. All right, I'm over on the portal. I'm going to open up a terminal, and I'm going to make a directory, CD into work, then classes, ME461, and let me just check, make sure. Okay, I actually have a class listed there. I want to make a new directory, make a directory L33, and then CD into L33. Okay, so now you want to download some files from Canvas. So we can grab, actually we'll grab all these files here while we're here and do them all at once. We're only talking about the Gauss quadrature right now. So we need to get the file explorer here, and then we'll put those files over here. Okay, now let's go back to our directory, and we should have 3 of those listed now. Great. Okay, so we have a couple of things to do to demonstrate this. The first is to load Mathematica. So module load Mathematica. and then you can just do Mathematica ampersand. Okay. And that should bring up a Mathematica example. And that should bring up the Mathematica user interface. Sometimes it takes a little time to load. Okay, when I bring that up, it says that the license is going to expire today. So I'll have to email the help desk about that. Hopefully it works. So we will open up that file, gauss.nb. This is called notebook. Okay. And we can actually, if you go to evaluation, you can evaluate the notebook. Okay, and this runs through all of these. These are called cells. Mathematics is kind of weird. It takes time to learn, but basically it's a numerical solver, you can see. So I have that in that page, and I'm going to now load MATLAB module. Load MATLAB ampersand. Okay, and I'm going to make this smaller here. Well, we might not need to. We can open this up, but actually I see a problem here in that we actually have to unzip these. So if you go back to this window, the Gauss int example is what we want. So you just do unzip, unzip, and then that directory, or that zip file. And what you do is you get a directory there. Okay, so now we can click on that folder. So now we're in here, and we have a Gauss integration example. So we'll actually load this. So open. All right. So this is Gauss quadrature of a 2D function, and this is actually a really interesting little problem here. So if you can see that this is actually kind of short. And if we go through it really quickly, what happens is we have the number of integration points, so 2 by 2. So that's what we just showed in the PowerPoint. Okay. Then it's going to call this function Gauss integration. Gauss integration, and it's going to get the integration points and weights. I'm going to skip that for now, just to say you have weights and points there. Okay. Then we have this flag I put down there for isoparametric. So what it does is we're only looking at one element, and so here it defines the coordinates of the node. So we're at -1, 1 basically. So we're the master element essentially, and we're looking at some value here. Value is equal to 0. We start, and then what we do is we start a loop, and it goes over the integration point. So this was 2 before, so it starts on that, and then it computes the sampling point in the x. So it has to figure out, all right, what is my psi value? Okay, and so it looks up what those were. These are actually computed dynamically and filled according to how many integration points you want, right? So they were filled up here from this function. So it reaches in, it grabs that, it grabs the weight point for the same integration point, and then it does that for the y value. So it does x, then it gets a y value, okay, and it basically does the same process. It grabs the eta value in this case. Instead of the psi, we're doing the eta. And then if it's isoparametric, so if isoparametric equals 0, which means it is not isoparametric, it must be -1 to 1. It basically evaluates this. It's going to take x is equal to psi, y is equal to eta, and then we have some function x squared plus y there. And then it's going to evaluate that. So the value is going to be equal to the old value plus the function times the weight. And that's actually from the equations that we showed before. So what is this? So this is actually using the master element. Okay, so our dimensions go from -1 to 1. So we can run this now. Let's see run. All right, so we get a value of 1.333. So let's go back to our MATLAB, which is it's a numerical solver, but it actually gave us the value of 4/3. I don't know the process, whether it's using the same process in there or not, but here we have x, our function is x squared plus y, and where you can see the domain is going from -1 to 1 also. Okay, so I'm doing the same problem in using a symbolic solver as I'm doing using Gauss integration, and what we see is that the answer is really accurate. Okay, so then you might want to say, all right, let's do an experiment. Let's make it go from 0 to 1. Okay, so we'll go 0, 0, 0 to 1, 1. Okay, so when we integrate that, let's evaluate the notebook again, we get a different answer. So this integral is 0.833. Now what happens if we do that in the Gauss integration example? So I have it set up here already. We can just comment this out and then turn on this. Okay, so there we're going. X is 0 to 1, y is 0 to 1. Okay, so the same bounds are given here. Let's run this example again. And what we do is we actually get the same answer. So you can see it actually gave the same answer there, and it does not agree with Mathematica. All right, so now let's actually demonstrate that the isoperimetric form works. So let's make this equal to 1. So now what's going to happen is that's going to trigger this loop. This is all going to stay the same, okay? But if isoperimetric equals 0, it's going to do this. Otherwise, it's going to do this. And so here, what we're doing is we're using those natural coordinates. We're defining shape functions, and we are evaluating all the internal element variables. So for example, the determinant of J, the J matrix, and then we use that to get our X value, use the shape functions and the isoperimetric form to get that transformed value. And then what happens is the same function is used, except we introduce the determinant of J here with the weights, just like the textbook said, and then we evaluate. So let's try running this. And there we see that we actually get the same answer now. So we've moved, and the reason, why does that work? Well, the reason is that we're trying to use basically Gauss integration over a domain that the mathematicians did not design it for. So it was designed to go from -1 to 1. And so if we go from 0 to 1, it messes up the solution. Okay, so that is why it works. And of course, I think I go on to do another example here. So if we actually change the function now, so let's turn that off and turn this more complex function. So we have x cubed, x to the 4th, x times x to the 5th. So it's a really complicated function. And we can even create a crazy domain. So looks like turn this one off and turn this top one on. Okay, so it's going 2, 11, 11, 2. So it basically looks like this integral, and we get, this is the integral from this crazy function, 2.51 times 10 to the 11th. So we have our x positions put in. We're going to be using isoperimetric form, which means it's going to transform it down to -1 to 1. And then we have our function here defined. So let's run this. And we get an answer that looks close, but let's now turn on some error here. Okay, so what I'm doing is I use this value here I got from this, so it's try to get it exact as possible because it actually evaluated this fraction. So then I'll run this again, and we see our percent error is 2.1%. Not bad. It's less than 10. That's definitely acceptable. We could possibly improve this. We could possibly improve this. Maybe if we jumped these integration points, let's say we had 3 integration points, okay, which are given by the textbook. Let's run that. And you can see the error goes down significantly, okay, by a whole bunch. So that's pretty exciting. I don't know, for me, this was like really helpful because you can actually see what Gauss integration is doing. By the way, this Gauss integration M file here, it's actually just a lookup table. So it's just getting the values, point X, gets them right here. So it gets actually, this looks up in a lookup table, and that lookup table looks very similar to what we had in the textbook. So you see the negative 0.577, the weight is equal to 1. So it basically just goes with the 3-point quadrature, 4-point, and so forth. So this is essentially that textbook, directly out of the textbook, that table. And then it populates these point X and weight X. And so it is really helpful. It's a short example, and it shows you how the internals work, at least for one element, and compared it to an analytic solution. So I hope that was helpful for you. Just another reminder that unlike the constant strain triangle, the stresses in the quadrilateral element are not constant either. Okay, so they're functions of psi and eta, and consequently vary across the element. In practice, these are evaluated at the Gauss points, which are also the points used for numerical integration. So we actually compute the stress. We have stresses and strains at each one of those Gauss points, just like we have for K. For the quadrilateral, this gives us, of course, 4 stress values. And then a lot of times what we do is to generate less data, especially for plotting, we evaluate the stresses at one point. And typically it's sort of at the centroid or the psi and eta equals 0 values. Okay, so I hope that was helpful. Let's now end this and now talk about defeaturing of CAD.